Hydrolysis of salt solutions. What exactly is hydrolysis of salt solutions? Hydrolysis of salt solutions, from the word hydrolysis, hydro meaning water and lysis, which means to break apart or split apart. Hydrolysis of salt solutions is a chemical process wherein salts dissolved in water react with water molecules, resulting in the formation of acidic, basic, or neutral solutions. This phenomenon depends on the nature of the acid and base from which the salt is formed, whether they are strong or they are weak. The hydrolysis involves the ions of the salt interacting with water, which alters the pH of the solution.
Wait, aren't there people who contributed to hydrolysis of salts? Who are they and what did they do?
Here are the proponents that contributed to the discovery of hydrolysis of salt solutions. So first on the list is Svante Arrhenius. Svante Arrhenius was the one who revolutionized acid-base chemistry by proposing the concept of electrolytic dissociation in aqueous solutions. He defined acids as substances that increase hydrogen ion concentration and bases as those that increase hydroxide ion concentration in water. So, acids that react with water, its hydrogen ion increases, while bases that react with water has its hydroxide ion concentration increase. His theory explained that salts dissociate into ions in solution, which can interact with water, foundational for understanding hydrolysis of salt solutions.
Gilbert and Lewis from 1875 to 1946. Lewis revolutionized acid-base theory by defining acid and bases based on electron pair acceptance or donation, broadening the concept beyond proton transfer. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor, covering reactions not involving hydrogen ions directly. So basically, Gilbert and Lewis and his contribution to hydrolysis of salts is he stated that acids is an electron pair acceptor while a base is an electron pair donor.
Next is Antoine Lavoisier. Lavoisier was the founder of modern chemistry. Although he didn't describe salt hydrolysis directly, he was the one who promoted the idea of chemical reactions involving water. Next is Justus von Liebig. Liebig was a German chemist who advanced agricultural chemistry. He explored the chemical behavior of salts in soils and water, influencing how scientists understood salt interactions, including hydrolysis.
Johannes Nicholas Bronsted and Thomas Martin Lowry. They both developed the Bronsted-Lowry acid-base theory. Their theory states that acids are proton donors while bases are proton acceptors. This helped clarify how salt hydrolysis occurs, especially with conjugate acids and bases from weak electrolytes. Jacobus van 't Hoff, Wilhelm Ostwald. Jacobus van 't Hoff and Wilhelm Ostwald introduced the law of chemical equilibrium, which explains how reactions reach balance, while Wilhelm Ostwald applied this idea to acids, bases, and salts, creating the hydrolysis equilibrium formulas. These formulas show that how salt ions react with water and determine if the solution is acidic, basic, or neutral. For example, KH equals KW over KA, or KH equals KW over KB. What are equilibrium formulas? For weak acid plus strong base, for example CH3COO negative plus H2O to CH3COO H plus OH negative. This solution is an example of a weak acid plus strong base. We must identify which comes from a weak acid because strong bases and strong acids isn't the one that was reacting to water, but rather the weak acids and bases. So in short, we must find the one that does react, or meaning to say, the weak acids and bases to water, which is CH3COO negative. The equilibrium constant KH equals HA times OH negative over A negative. Relationship between Ka and Kw. The KH for this reaction is mathematically equal to the base ionization constant Kb of the anion. This is directly related to the acid dissociation constant Ka of the parent weak acid HA and the ion product constant of water Kw. KH equals Kb equals Kw over Ka. Ka means acid dissociation constant, while Kb means base dissociation constant. Kw means ionization constant of water, and Kh means hydrolysis constant. This results into a lower Ka, weaker parent acid, which leads to a higher Kh or a stronger hydrolysis, which means more basic solution. For strong acid plus weak base, we have an example of ammonium chloride or NH4Cl, where the acidic cation hydrolyzes. The ammonium ion B+ is the conjugate acid of a weak base BOH, so it reacts with water to produce hydronium ions H3O or H+, making the solution acidic. B++ H2O to BOH plus H+. The hydrolysis constant KH is KH equals BOH times H plus over B plus. Relationship of Kb and Kw, the KH for this reaction is mathematically equal to the acid ionization constant Ka of this cation. This is directly related to the base dissociation constant Kb of the parent weak base BOH and Kw. KH equals Ka equals Kw over Kb. This results into a lower Kb, weaker parent base, which leads to a higher KH, meaning more acidic solution or a stronger hydrolysis. For weak acid plus weak base, ammonium acetate CH3COO NH4, where both the cation and anion hydrolyze, both the cation and the anion react with water. A negative plus B positive plus H2O is to HA plus BOH. The equilibrium constant KH is equivalent to HA times BOH over A negative times B plus. Relationship to Ka, Kb, and Kw, in this case the total hydrolysis is a combination of the two previous effects. Kh equals Kw over Ka times Kb. Determining pH, the final pH depends on the relative values of Ka and Kb. If Ka is greater than Kb, the solution is acidic. If Kb is greater than Ka, the solution is basic. If Ka is equal to Kb, the solution is neutral. Take note, for salts of a strong acid plus a strong base, for example NaCl and KBr, neither ion hydrolyzes, so KH is negligible. And the solution remains neutral, pH equals 7. This means that the strong acid cannot give a hydro ion, while the strong base cannot take a hydrogen ion.
So, how do we do hydrolysis of salt solutions? There are 3 steps in doing hydrolysis of salt solutions. First step is to identify the strong
What is
elements.
hydrolysis for?
The second is to
Hydrolysis
dissociate
is for
the salt ions.
and mainly
the third
used
and
to
last step is to
identify the
identify
acid's pH
whether
level
it
when
is
it
neutral,
dissolves
acidic,
in water,
or it's basic.
if it is acidic,
For the first
basic,
step,
or neutral.
There isn't no formulas to do,
So,
but rather
how do we do this?
familiarizing or memorizing which belongs to which, like which belongs to the strong acids, which belong to the strong bases, and so on. So for example, there is a list here of those included in the strong acids and the strong bases, as you can see in the screen.
Step 2. Dissociation of the salt. For example, CH3COOH plus NaOH. If we would neutralization reaction, it would be CH3OOH plus NaOH. CH3COOH is a weak acid because it does not you cannot see CH3COOH from the strong acids, meaning to say it is a weak acid. And NaOH is a strong base because you can see in the table of strong bases, the 8 strong bases, you can see NaOH. So NaOH is a strong base. CH3COOH plus NaOH to Na negative plus CH3COO plus. Na is negative because Na is positive because it is a metal, while CH3COO is negative because it is a non-metal. CH3COO would be negative because if you dissect that compound, it would be CH and O, which are non-metals, and Na would be positive because it is a metal. We got to identify if it is non-metal or not because non-metals are negative and all the metals are positive. You can check if they are metals or non-metals at the bottom left part of the periodic table. A few minutes ago, we mentioned the process where we do this part in dissociating the salts CH3COOH to NaOH. This process is called the neutralization reaction. You may ask yourself, what is neutralization reaction? Well, you see, neutralization reaction is a chemical process where an acid and a base react with each other to cancel out their acidic and basic properties, producing salt and water and forming a solution that is closer to neutral in pH. So as you can see a slide ago, you identified that CH3COOH is a weak acid because you cannot see CH3COOH in the strong acid group. Then you concluded that it is a weak acid. That is what you call neutralization reaction. What about the part where you mentioned dissociation reaction? What's that? It's a chemical process where a compound breaks apart into 2 or more smaller particles such as atoms, ions, or molecules, usually when dissolved in water.
here we have a strong acid and a strong base. So since strong acid and strong base, if you plus them together, then that means it is neutral. Okay, next we have an example which is HCl plus NaOH. HCl is, we need to find HCl in the strong acid group of 7. Since HCl is part of that group of strong acids, those 7 strong acids, then that means it is a strong acid. NaOH, if we look at the table of strong bases and find NaOH, then that means it is a strong base. So next, since we are putting the acid into water, then that means we need to put H2O, since this is hydrolysis of salts. H2O, or water molecule, plus if we dissociate NaOH, then that means it would be Na. But since it is a metal, then that means it is a positive. If it weren't a metal, then that means it would be negative. But since it is a metal, so that means it is positive. Plus, if we dissociate HCl, then that would be Cl minus. Since Cl is a non-metal, then that means it is negative. So, if we look at NaOH as a strong base and Na, we can say Na is a weak conjugate acid, because NaOH is a strong base, and if it is a strong base, then that means it is a weak conjugate base, because then again it is a strong base, and as a conjugate acid it is weak. So if we look at HCl and then Cl here, HCl is a strong acid. So meaning to say, if as a base, as a conjugate base, it is a weak conjugate base. Why? Because, as I said, as a strong acid, HCl, then that would conclude that as a conjugate base, it is weak. Okay, so if we would imagine chlorine ion plus a water molecule, H2O, then that, since it is a weak conjugate base, it cannot generally take a hydrogen ion from the water molecule. So this is A, D, and D. So if we look at Na, or sodium ion, plus a water molecule, we would see that since it is a weak conjugate acid, then that would mean that it cannot give a hydrogen ion to H2O, or the water molecule. We need to remember that weak conjugate base cannot take a hydrogen ion, and if it is a weak conjugate acid, then it cannot give a hydrogen ion. But if it is a strong conjugate base, then it can take a hydrogen ion. Same goes to Na. If it is a strong conjugate acid, then it can give a hydrogen ion to the water molecule. So since these are both weak conjugate bases and acids, then it cannot be, or D and D.
Here we have an example of a strong acid and a weak base. If it is a strong acid and a weak base, we can say that this is acidic. Here we have an example of this acidic solution, HCl plus NH4OH. Now we need to identify if it is a strong acid or a weak acid. HCl. If we look into the group of 7 strong acids, we can conclude that HCl is part of that strong acid. NH4OH. If we then again look into the groups of 8 strong bases, we can conclude that this is a weak base because you cannot see NH4OH in the strong bases. If you would dissociate this, if we would dissociate NH4OH, then that would be NH4. Since it is a non-metal, then that means we can say it is negative. Plus Cl. Cl minus, because then again, it is a non-metal. If it were a metal, then that would be positive. But since it is not, it is negative. If we look into the weak base and the conjugate acid, we can conclude this is a strong conjugate acid, because then again, NH4OH is a weak base, and as a conjugate acid, it is strong because it is a weak base. Strong conjugate acid because it is a weak base. If we look into HCl as a strong acid and look into the conjugate base Cl, we can say it is a weak conjugate base. Because then again, the reason for this being a weak conjugate base is because this is a strong acid. Now, we need to ask ourselves, what would happen if we put chlorine ion with the water molecule H2O? Since this is a weak conjugate base, it cannot take a hydrogen ion. It cannot take a hydrogen ion. So if we look into NH4 ion plus a water molecule H2O, since it is a strong conjugate acid, then it can give a hydrogen ion to the water molecule. So this is good. This is A. This is D and D. So since ammonium ion can donate a hydrogen ion to the water molecule, so that means this would be H3O plus NH3. So this proves that this solution is acidic. This also proves that NH4 hydrolyzes with water. Here we have a weak acid and a strong base, which means it is a basic solution. CH3COH. If we look into the strong acids group of 7, we cannot find CH3COH. So that would conclude that it is a weak acid. Now, if we look into NaOH and look into the strong base of 8, bases of 8, we can find NaOH, which concludes to be a strong base. So now we have to dissociate this problem. H2O plus Na. Since this is a metal, this can be positive, plus CH3COO minus. Minus because if you would dissect this would be carbon, hydrogen, and oxygen, which are non-metals, so that means it is negative. So now we have to find the conjugate acid of the strong base. Na conjugate acid. If we look into NaOH as a strong base, we can conclude that Na is a weak conjugate acid because NaOH is a strong base, and as a conjugate acid, it is a weak conjugate acid. Okay, so if we look into CH3COO minus and look into the weak acid, which is CH3COOH, we can conclude that this is a strong conjugate acid, a conjugate base. Because then again, it is a weak acid, so that would mean that it is a strong conjugate base. So now, if we put CH3 COO negative plus a water molecule H2O, we can conclude that since it is a strong conjugate base, then that would mean it can take a hydrogen ion from the water molecule. So that would be CH3COO plus OH negative, and this is positive. Wait, it's just CH3COO. So it is CH3COO negative plus H2O. H2O gives a hydrogen ion to CH3COO, which makes it CH3COOH plus OH negative. Negative since nakuha na siya hydrogen ion. So now we have to check for Na. Na plus hydrogen water molecule H2O. So since it is a weak conjugate acid, then it cannot give a hydrogen ion to H2O. So meaning to say, it cannot be. For D and D. This solution proves that this is CH3COOH plus NaOH is basic.